So here are some examples of two-dimensional motion problems. So some general notes: if ever you see a vector, break it into components. This is a very important step, and it'll happen a lot. Use both sets of your equations. You have x and y components, use them. Okay? And then the third part, work with your variables first, except zeros. This makes debugging your problem so much easier, and you can follow through what's going on. And we'll see a really good example of this in a moment. So there are three motion equations we're going to use. And I'm going to use subscript x, but you can use whatever subscript x or y that you need. So the first one is your final velocity is equal to your initial velocity plus your acceleration times time. Your second equation, which turns out to be one of the more useful ones, your x final minus your x initial equals your initial velocity in that direction times time plus 1/2 ax t squared. Now in the x equation for projectile motion, this is really useful, as when this a goes to 0, works out alright, makes things a little bit easier. And then your third equation that you're going to use is when you don't have time, and that's v final squared plus v initial squared plus 2 times your acceleration times your change in x. And remember that this change in x is just your final x minus your initial x. So let's see what we can do with these. Now before we jump right in, here's a couple things you should know. First thing you do, write down your givens, your unknowns, and draw a picture. So this gives you a very nice setup to work with. Alright, lets you know what's going on. Next, think about the principle and the idea. So this kind of gets you thinking about, oh, where should I look? What type of problem and what type of formula are you going to use? Right? When you look at that formula sheet, the one that's posted on Blackboard, I would always have that with you, by the way, whenever you're working homework. It's the same one we'll use on exams. This gives you an idea of where to look. Finally, after you know where to look, do your equation and then check your solution. And ask yourself if this makes sense. The key part of physics is tying in this math to the physical world. So we want all of your answers to make sense to you. Alright, so pause a minute, read the question, draw your own picture, and then pause for a second, we'll resume, and we'll go back where we started. And I'm going to draw this little picture. So we have a baseball player who hits a ball up over a fence, and it's a home run, and the crowd's going wild, and it's very exciting. It's also an exciting time for physics. So that is 35 degrees at this angle. And that angle is going at some, or that is the angle for some v naught. All right? And as you know, this v naught has v naught x and a v naught y component. So if we write down everything we know, x naught is 0. X final, well, it's 130 meters away, so that's going to be 130 meters. V naught x, well, we don't know it, but what you can do is you can relate v naught and this angle, and that's just as good most of the time. So we'll say that this is equal to v naught cosine, because you want the x component, cosine of theta, and v naught. Likewise, v naught y, we break that into components, we're going to get v naught sine of theta. Acceleration in the x direction is 0, time, we don't know, ay is just gravity, negative 9.8 meters per second. Don't know vy, v final, 21 meters, and y initial, 1 meter, because it starts 1 meter across the ground. So that's the setup for this problem. Now we're going to walk through, and it's going to be kind of, okay, it's a lot of algebra, I'm not going to even kid you about this, but if you go through and systematically work it, everything is going to be okay, which is another rule of physics: don't panic. Okay, so what we're going to solve for, we are going to solve for v naught, the initial speed of the ball. Now, as you look at these equations, you will notice that maybe it'd be really helpful to have time. So what we're going to do is we're going to solve for time in terms, so we're going to solve for time in terms of something else. And I picked the x side just because it looked a little easier. So if we start with x minus x naught equals v naught x t plus 1 over half ax t squared. Again, we look for some zeros. X initial is 0, ax is 0. And this is why I picked the x side, because it had those zeros. And you get x final over v naught x equals t, which equals x over v naught cosine of 35 degrees, or cosine theta. So keep that in mind, and we're going to plug this in our next part. So now we have an expression for t. And now comes the math-intensive part. So we're going to use our y equation. We're going to say delta y. And I'm using delta just because it's a little easier to carry through. V naught t plus 1 over half ay t squared. Okay, so we're plugging in this expression for t, and we get delta y equals v naught sine theta x over v naught cosine theta plus over half, make sure that plus looks good, ay t squared. So now we're going to combine some terms. So the first thing I want you to notice, your v naughts are going to cancel. So if we combine this, and I'm going to bring those over, so we get delta y equals x. And if you remember, sine divided by cosine, remember what that function is? That is just tangent. I'll just leave that as theta, 35, plus 1 over half ay t squared. If we move that over, we get delta y minus x tangent theta equals 1 over half ay, and I'll put that x over v naught cosine theta squared. And now we're going to pull up a new slide, which you don't need to necessarily do at home. Okay, so we're going to keep on working with this. Keep on keeping on. That's generally how it goes. So we'll say, now we have 2 times the quantity, delta y minus x tangent theta over ay. So we're just getting rid of this part. Okay, now we're going to continue to work this, so we'll get x squared on the bottom, cosine squared theta on top equals 1 over v naught squared. So we're going to invert and take the square root, so we get v naught is equal to, that was a lot of work we're doing, ay x squared over 2 delta y minus x tangent theta cosine squared theta equals, plugging in numbers, I'm just going to do this so I can put the negative 1/2, 9.8 130 squared over 2. Delta y is 20 because it's 21 minus 1. 20 minus 130 tangent 35 degrees times cosine squared 35 degrees. Continue that line. 1 over half, and you get your v naught equals 48.3 meters per second. Awful lot of work, but that answer was worth it, and you got some really good physics experience. So we're on the home stretch now, and we just need to solve for time. And we can use any equation we want. So I am personally going to use the x equations because they look a little easier to me, x minus initial x equals v naught x t plus 1 over half ax t squared. Plugging in our zeros, we know that that's 0. We know acceleration in the x direction is 0. And we get x over v naught x equals t, which equals 130 meters over 48.3 meters per second times cosine 35 degrees. And when you plug this in, you will get 3.29 seconds. So I hope that was helpful. A couple extra examples than the ones we have in class. If you have any questions, if you're getting different answers, please come stop by and see me. And I hope that this helps.